Hi, everyone. Today we are going to be focusing on section 3.4, velocity and other rates of change, and in particular, the idea of the concepts of motion. So we're going to start off with this handout that I've given you. We won't get through the whole thing in the video. We will work on the rest of it tomorrow in class. So hopefully you get a basic understanding now, and then we'll charge it up a little tomorrow in class. Okay, so we have three concepts of motion we want to talk about: position, velocity, and acceleration. I've already typed up a lot of it so that way you can read it a little bit better. Obviously, if you need to, you can pause so that you can copy everything down. So the first concept of motion is what we call the position. And when we're talking about this, we're talking primarily about a particle that's moving along the x-axis. So if the particle is moving along the x-axis, then the position, which we usually call x of t, determines where the particle is located on the x-axis at any given time. So think of something moving just right or left, and then you substitute a time in and it'll tell you exactly where it is moving right or left. Then we have velocity, and so velocity is written either as x prime of t, so the derivative of x, or it has its own way of writing it as v of t. And velocity then determines how fast the position is changing at a certain time, sometimes called instantaneous velocity. So you'll want to know, is it changing its position quickly, slowly? What direction is it moving? All of these things velocity will tell you. And then acceleration is either the second derivative of position, the first derivative of velocity, and it can be written as a of t. And this determines how fast the velocity is changing. So sometimes it's a little harder to understand, but it is understanding is the speeding up or slowing down. Okay, so now I have a whole bunch of vocabulary words, or not even vocabulary words, but ideas to go along with it. And it's just easier if we kind of just talk about them real fast here, write them down so you have them to look back at, and then we'll do some practice problems with this information. So when you hear some of these phrases, you want to understand what they mean. So the first phrase that you want to understand is if we say initially, what we really mean is that time is zero. So initially means is when time is zero. At the origin now means, so time is zero and the position is also zero. The x position is also zero. So it still feels like 0, 0, but remember we're moving only along the x-axis here. And then if the particle is at rest, so if we say the particle is at rest, then what we really mean is that the velocity is zero, so it's not moving. Okay, and then these next few phrases we'll use a lot, and we'll continue to use them, and you'll hear them asked on the AP exam as we start reviewing later on in the year. You'll see them again and again. If the velocity of the particle is positive at any given time, then the particle is moving to the right. So positive velocity moving to the right. If the velocity of the particle is negative, so think negative speed from physics, then the particle is moving to the left. If the acceleration of the particle is positive, okay, so second derivative is positive at a given time, then the velocity is increasing. So velocity is getting bigger, Okay, that's all I need to say about that. If the acceleration of the particle is negative, then the velocity is decreasing. These four concepts, again, we're going to hit on a lot. Okay, a couple things about the word average. Remember that average is calculated like slope. So average velocity would be displacement over time. So the change in the position over time would be another way to think of it. So displacement is the distance that you've moved, but not taking into account if you've moved to the right and then to the left. Average acceleration then would be just the change in velocity over time. So we've got change in distance over time, and then acceleration is change in velocity over time. Average acceleration. All right, and then instantaneous velocity, then, as you know, instantaneous means something to do with the derivative. So instantaneous velocity would be the velocity at a single moment. And then keep in mind that if the velocity changes sign, that means that the velocity has changed, is stopped at some point in time. So if you go from a negative velocity to a positive velocity, in between those times, the particle should have stopped or been at rest. Okay, that's a whole bunch of information. Like I said, if you need to pause the video or make sure you've copied it down correctly. And then we're going to go ahead and do 3 different examples. We're going to do kind of an analytic example in AP style. We're going to do more of a numerical, so like with a table kind of style. And then we're going to do one with a graph. And this is really something that AP wants you to be good at, being able to analyze information in those different formats, whether it's analytically, graphically, or with a table. Okay, so here's the first example. And it is broken down for you in pieces, like one, two, three, four. Um, Sometimes we'll just ask all the questions in one sentence. All right, so we're going to see how well I'm going to be able to write with this pen today. Okay. One way to determine total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all resting points. This is actually going to relate to the very last question in this information. So a particle moves along the x-axis at time t, so its position is given by this function. So at time equals 0, we want to know, is the particle moving to the right or to the left? So remember that this actually relates to the velocity. So if the velocity is positive, you're moving to the right. If the velocity is negative, you're moving to the left. So we need to find the velocity, which is the derivative of the position. So the derivative of this function is 3t squared minus 12t plus 9. And we could simplify this if we wanted to, but all we really need to know is what the value of the velocity is at time equals 0, which is pretty easy to calculate from here. So you'll see that the velocity at time equals 0 is 9, which is greater than 0, so it's positive. Since the velocity is positive, this means that the particle is moving to the right. Okay. So now the second question says, is the velocity of the particle increasing or decreasing? So remember, increasing or decreasing velocity is related to the acceleration. So I need the acceleration of this function. So I need the derivative of the velocity. And the derivative of the velocity is 6t minus 12. And I now want the acceleration at time equals 1. Okay, so I'm substituting 1 in, and I get negative, should probably have calculated this first. 6 minus 12 is a negative 6. Is that a true statement? So since this is negative acceleration, then we know that the velocity is decreasing. Ooh, I didn't spell that right. Decreasing velocity. Okay. Finally, the next question says, find all values of t for which the particle is moving to the left. So again, we want to know if it's moving to the left, we know that the velocity is negative, but we want to know all of them. So what I need to do is take the velocity and set it equal to 0. And that's this thing up here, 3t squared minus 12t plus 9. I'm actually going to factor this. So I'm going to factor out a 3. And then I'm going to factor the quadratic here, and that factors into t minus 1 times t minus 3. So what this is telling us is there are 2 places where the particle is stopped. So where the derivative equals 0 is where the particle is stopped. T equals 1 and t equals 3. So what we want to know is in between or to the left and right of those values, is the velocity positive or negative? So I'm going to do a number line test with this. So time starts at 0. Then I have the 1 and the 3 that are important. These are the places where it's crossing the x-axis, so where it's stopped. I'm testing this on my velocity. So I'm just going to substitute values. And you should remember doing this from pre-calc even last year. So I'm going to do like a half. So substitute a half in here. I get a negative times a negative, which is a positive. Between 1 and 3, like 2, I put 2 in here. I get positive times negative, which is negative. And then something to the right of 3, like 4, would be positive times positive, which is positive. So this time in here is when the velocity is negative. So since the velocity is negative between 1 and 3, the particle is moving to the left from time goes from 1 to 3. Now, if this were an actual AP test, we'd have to do a little bit more wording than just this. We'd need more information than this. But we're going to get to that tomorrow. Okay, number 4 says find the total distance traveled by the particle over the time interval. So total distance traveled, then we have to take into account the direction that it's going. And so basically what I'm going to do is use those 3 values that we have up there and calculate them out. But I'm going to calculate their position, okay? So at time equals 0, the position of the function. So I'm going back up to that t cubed minus 6t squared function. When I calculate that, I get x of 0 is equal to 4. So the position is 4. I'm actually going to draw a quick little number line sketch of this. That's a bad line. So at time equals 0, we're starting at 4, okay? Then at time equals 1, again, calculating it out, I'm going to get 15. So the particle travels from 4 all the way out to 15. I don't like where I wrote that. Okay, and then at time equals 3, when I calculate that, I get 11. So what that means is the particle moves backwards to 11. So it goes from 4 to 15 and then back to 11. I only want to use these absolute value distances. I do not want to use their actual negative or positive value. So from 4 to 15, we went a distance of 11. 15 minus 4 is 11. And then from 15 back to 11, we went a distance of 4. So the total distance traveled is 11 plus 4, which is 15. Okay. All right, that's our first example. Second example is one using a table. And the table you want to read carefully says that it is the velocity function that we are looking at. So make sure that you think about velocity and what that means as we do these problems. Okay, so the first question says at time equals 0. By the way, take a moment to look at the data before you start. So notice what's happening. Again, just like I said, read the information, read that this is a velocity in meters per second, and so forth. Okay, so the first question says at time equals 0, is the particle moving to the left or to the right? Well, that means I want the velocity at time equals 0. The velocity is a -3. Since the velocity is negative, then the particle is moving to the left because we have a negative velocity. Okay. Is there a time during the interval 0 to 12, when the particle is at rest? Explain your answer. Okay, so it's at rest when it changes from negative to positive. So that when the velocity changes from negative to positive. Please don't use the it word like I just did because that doesn't describe anything. So when I look at the table, I see that the velocity is at -3 at time equals 0 and 2 at time equals 2. So sometime between 0 and 2, it crosses the x-axis, and that would be where it would be at rest. So the time interval where it is um, at rest would be between 0 and 2. And it's at rest here. So here's kind of some wording we would use because v of 0 equals -3 and v of 2 equals 2. Change a sign in there. Or the velocity goes from negative to positive. Okay, use the data from the table to find an approximation for v prime of 10. So v prime of 10, the approximation really could come from using the values to the left and to the right of 10 for the actual velocity. So I'm going to do v of 12 minus v of 8 over 12 minus 8. This simplifies to be -1/2, and that is meters per minute squared. Okay. So what does this mean in terms of the motion of the particle? Well, the acceleration is negative. So since the acceleration is negative, the velocity is decreasing. Okay. So now in 4, it says A of t denotes the acceleration of the particle. Is there guaranteed to be a time in the interval that the acceleration is equal to 0? Okay, first of all, this is a differentiable function, which means that it's continuous. Okay, so there's no jumps, holes or gaps. So when I look at this data, I see that between 8 and 12, and maybe I'll go back up and show you the data again. Between 8 and 12, the velocity is decreasing, right? So it's going from 7 to 5. So what it's changing from increasing to decreasing, I guess would be another way to say it. So therefore, since this is happening, there must be a place where the derivative of the velocity is equal to 0. It also helps. So let me finish that statement first. So yes, um, velocity changes. And I don't even like that wording as much. I'm going to keep it, but there's probably other ways we can state it as well. So velocity changes from because velocity is not really decreasing; it just changes. It slows down. Really, is what's happening. Okay, so if we were to think about where the values were at, so at 8 we have a value of 7 on our graph, and at 12 we have a value of 5. Okay, but then if you go back a step at 6, oopsie, let me put a dot there and the 5 over here. We also had a value of 5. So basically what we know is happening is the velocity is going up and coming back down. So there has to be some sort of a maximum up here, which would cause the acceleration to be equal to 0. So that's really, I think, helpful to look at the graph of that. Even though this is a tabular method, thinking of it graphically, I think can help a lot. Okay, the last one is a graphical approach, and then we're done with the video for today, and we'll pick this up tomorrow. So we have this graph. Again, look at the graph carefully and notice that the information is talking about the velocity in feet per second over the interval 0 to 9. So we're looking at velocity graph. Okay, so the first question is, at time equals 4 seconds, is the particle moving to the right or to the left? Well, it's moving to the right because v of 4 v of 4 is greater than 0. That's all you need. That's a 4. Okay, over what time interval is the particle moving to the left? So now you want to see when is the velocity negative on this picture. So we're going to go from 5 to 9 because this is where the velocity is less than 0. So if you go back and look at the graph, 5 to 9 is where it's negative, where it's below the x-axis. Okay, at time equals 4 seconds, is the acceleration of the particle positive or negative? So the acceleration is negative because v of 4, so the velocity at time equals 4, is decreasing. Okay, or what you could look at is that the slope at 4 is negative. So I'm going to go back up and look at the graph again. So at time equals 4, I have a positive velocity, yes, but the slope, the actual graph is decreasing. So the acceleration, remember, this is velocity, right? So if you were to take the derivative, just do it with normal slope, you would see that the acceleration would be negative because the slope of that line is negative. Okay. Oops. So slope is negative. What is the average acceleration of the particle over the time 2 to 4? So this literally means I'm going to do v of 4 minus v of 2 over 4 minus 2. And I'm just going to get negative 3/2 feet per second square because I have just found the acceleration. Don't forget which is how you write units. Okay, so we know that the average is this, but do we know that there will be a time where the derivative of the velocity, an exact time where the derivative is equal to negative 3/2 feet per second squared? And the answer to this is no. And this is because the velocity function is not differentiable. So it's got those corners on it. So the corners are what's going to cause the issue. So if you look at the derivative of the velocity on 2 to 4, I'm going to draw a quick awful sketch, sorry. So from 2 to 3, the slope is, I believe, 3. So from 2 to 3, I have just this horizontal line. But then from 3 to 4, the slope is -6. And there is no connection between the two. They don't cross the x-axis. So therefore, you will never have a place where the acceleration at an exact time where it's equal to -3/2. All right, and final question for this video. At what time t in the given interval is the particle farthest to the right? So this comes from looking at the graph and looking at all this positive velocity. So positive velocity, positive, 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 positive. So when you have a positive velocity, remember that means the particle is moving to the right. Okay, so all this is particle moving to the right. When we hit 5, now all of this is negative velocity, and that means that the particle is now moving to the left. So after time equals 5, we've stopped moving to the right and we're going the other direction. So it'll be the farthest to the right at time equals 5. Because at 5, the particle changes direction. All right, I hope everyone understood that, but make sure that you come to class with any questions that you might have for tomorrow so that we can clarify any issues that you might have. Have a good night.